Hello and welcome to Auten Math. In this edition of Auten Math, we're going to talk about combinations. So let's get started. Okay, so the first thing I want to talk about is permutations versus combinations. So we said we're going to talk about combinations. Let's talk about permutations versus combinations. So I have an event, and the event was a baking event. And we determined there are 6 different recipes that were cooked. And we had Sally, David, Joe, and a couple other students who did some of the work and made some different baking items. And then we rated each of the different baking items for first, second, and third. And in the first item, Sally came in first, David came in second, and Joe came in third. In the second, Sally was first, Joe was second, David was third. In the third, David first, Sally second, Joe third, and so on and so forth. And you can see that for each of the 6 different events, we had a different arrangement of first, second, and third, but those people were all the same, Sally, David, and Joe. Now we had 2 other contestants, Sam and Bill, but because they did not do as well as we expected, they came in 4th and 5th respectively. And they weren't really counted as part of the first, second, and third place. All right, so when we talk about permutations, we talk about events in which order matters. So Sally, David, Joe would be an event for a permutation. Sally, Joe, David, because it's different than Sally, David, and Joe, would be another event for a permutation. So in this case, I would have 6 different permutations because all of these events are unique. None of them are repeated, because in no case do I have Sally, David, and Joe again, even though I have the 3 same people within the next 5 events, just in a different order. For a combination, however, if I talk about a combination, and a combination, this would just, all 6 of these would be one event for a combination. So for a combination, it would just be one event, because in a combination, order is not important. Right? Sally, David, and Joe is going to be the same as Sally, Joe, and David. So a combination, I have just one event, but for a permutation, I have 6 different events. Right? So let's keep that in mind. For a permutation, order is important, so first, second, and third is important, but for a combination, it doesn't matter who's in first, second, or third. What matters is who is in the group of 3. And since we have the same 3 people in the group of 3 each time here, then this just becomes one event for a combination. But in a permutation where order is important, I have 6 different outcomes. All right, so let's talk about combinations more specifically and take some examples. All right, so a combination. So combination is a selection of R objects from a group of N objects where order is not important. So again, permutations, order is important. For a combination, order is not important. And the formula for a combination is going to be n factorial divided by n minus r factorial times, this is a little times, a symbol for times, or multiplied by r factorial, where I would say n objects, and I'm going to choose r objects from those n objects. And I write this C here, so this is shorthand for combination. N would be the left-hand subscript, r would be the right-hand subscript. So I'm choosing R objects from a total group of N objects. So again, C is the combination, R is the number of objects that I'm selecting, and N is the number of objects I'm selecting from. And the formula again is n factorial divided by n minus r factorial times r factorial. So let's take an example. I have a 52 card deck. How many different 5-card hands are possible? So in this case, I'm going to end up with a combination of 52, and I'm going to choose 5. So the result is going to be n factorial, which is 52 factorial, divided by 52 minus 5 factorial, and then all multiplied by 5 factorial. So that gives us 52 factorial over 47 factorial times 5 factorial. Right, and the 5 factorial is part of the denominator. Now, I've talked to my students about writing or determining the value of a combination or permutation without a calculator. So let's go ahead and take care of talking about how we would do this, in this case with a 52 card deck and the 5 card hand example. So I have 52 factorial over 47 factorial times 5 factorial. Now 52 factorial is the same as 52 times 51 times 50 times 49 times 48 times 47 factorial, right? 47 factorial, 46, 45, 44, etc. And this is all over 47 factorial times 5 factorial. So I see 47 factorial and 47 factorial the same. And then I can evaluate 5 factorial very easily. 5 times 4 times 3 times 2 times 1 gives me 20, 60, 120. So 5 factorial becomes 120. So now all I need to do is multiply 52 times 51 times 50 times 49 times 48 divided by 120, and you should get a number that's roughly 2.6 million, a little bit less than 2.6 million. All right, so if you don't have a factorial button on your calendar, you can certainly use this approach where I eliminate the 47 factorial value, or 47 times 46 times 45 and below, which is common factors for both the 52 factorial and the 47 factorial. And I can simply evaluate 5 factorial, use my calculator, and then solve for that problem. All right. So we talked about combinations which are straightforward. Now there are a couple of combinations you need to know about that are not necessarily straightforward. And the first is when a question asks to find the number of ways event A and B can occur, then what you're going to consider is to multiply the combination of A to the combination of B. So let's take an example. I have a student senate. It consists of 6 seniors, 5 juniors, 4 sophomores, 3 freshmen. How many different committees of exactly 2 seniors and 2 juniors can be chosen? All right, so I have 2 different combinations, one of seniors and one of juniors. On the first combination, I have 6 seniors, and I'm going to choose 2. And I'm going to multiply that by, because I need to have and, right? I have exactly 2 seniors and 2 juniors, so I'm going to multiply the 2 combinations together. And in the second case, I have 5 juniors, and I'm selecting the 2. So in the first combination, I have 6 factorial over 4 factorial times 2 factorial. And that gives me 6 times 5, which is going to be 30, divided by 2, which is equal to 15. And I'm going to multiply that by 5 factorial over 5 minus 2 factorial, which is 3 factorial times 2 factorial, which gives me 5 times 4, which is 20, divided by 2, which is 10. So 15 times 10 gives me 150 different committees of 2 seniors and 2 juniors. So again, when I'm finding the number of ways event A and B can occur, I'm going to multiply the 2 combinations together. All right. Second possibility for, or unique, let's say, instance in using combinations is when the book or a question might ask how many different ways event A or B can occur. So remember, we had A and B, we multiplied. When we have A or B, we're going to add the combinations together. So when finding out the number of ways event A or B can occur, we'd add the combination of A to the combination of B. All right, so the example we're going to use is from a 52 card deck, how many 5 card hands are going to contain all hearts or all diamonds? Well, we know that there are 4 suits in a 52 card deck. We've got spades, hearts, diamonds, and clubs. So each of the suits has 13 different cards. And what we want to do is figure out in those 13, how many combinations can we have of 5 hearts and 5 diamonds, or 5 diamonds. So it would be a combination of 13. We'll take the hearts first, and I'm going to choose 5 of the hearts. And then I'm going to add another combination, 13. I have 13 possible diamonds because there are 13 diamond suits in a 52 card hand, and then I'm going to choose 5. So now I just have to evaluate the 2 combinations. I have 13 factorial over 13 minus 5 factorial, which is 8 factorial, times 5 factorial, plus 13 factorial over 8 factorial times 5 factorial. And I'm going to go ahead and pause for a second while you figure this out. And I'm going to come back, and then we'll provide the answer for you and move on to our last topic of discussion. Okay, if you do this correctly, you should get an answer 2,574 for both of these, for the sum of these two combinations. All right, so we're going to move on to the last concept. And this tends to be the more tricky of the three for most people. So we talked about when finding the number of times event A and B can occur, we multiply. When we find the number of times event A or B can occur, we add. And then when we're asked to find at least or at most the number of times an event can occur, then we're going to consider using subtraction to find the value. Now, why is it? We don't always have to use subtraction, but we're going to consider it because it might be the easiest way to go. All right, so the example is going to be we are going to toss 10 different coins, and how many ways will at least 4 of the coins show heads? Now, I can go through the process and say I have a bunch of different combinations. I have a combination of 10 coins. I can select 4 of those that are heads. Then I can add 10 coins, 5 that are heads, 10 coins, 6 that are heads, 10 coins, 7, 10 coins, 8 that are heads, plus 10 coins, 9 that are heads, 10 coins, all 10 are heads. Now, and I can add all these together, and I have 1, 2, 3, 4, 5, 6, 7 different combinations to calculate. Now, there is an easier way to do this, and really what we want to do is we want to find out the total number of possible combinations, including heads and tails, and then subtract those that I have that are not in the set, so those where I get 3 or fewer heads as part of the result. So let me go ahead and talk to you about how that would work. So when I toss my first coin, I have 2 different outcomes. The first is heads, and the second is tails, right? In my second toss, I have I can either choose heads or tails. Third toss, heads or tails. Fourth toss, heads or tails. Fifth toss, heads or tails. Sixth, seventh, eighth, ninth, and 10th. I think I got 10 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So I have 2 times 2 times 2, 10 times, which is really 2 to the 10th. So I'm going back to my counting principle again, what we've learned in the first section of this chapter to figure out the total possible number of outcomes. And then I'm going to subtract the number of outcomes which are not in the set. And that's going to be where I have a combination of just 3 heads out of the 10 tosses, plus a combination of just 2 heads, combination of just 1, and a combination where I don't select any heads at all, I just select tails, or I flip tails. All right, I'm going to subtract from the total. I have a total number of outcomes. These are total number of possible outcomes. And this is the outcomes which are not in the set. So I really have these 2 alternatives. I have this is the first possibility, and this is the second way to answer the question. And both of these are fine, but in the limit you're calculating 7 different combinations. In this you're calculating just 4. So sometimes when you hear at least or at most, you want to consider using this process because this is going to be the easiest process to undertake in order to solve the problem. So I'm going to pause here. You can figure out the answer to this, and then we'll be done for this section on combinations. All right, so you should get for total number of possibilities 1,024. For the first combination, 120. For the second, 45. For the third, 10. And for the last, 1. So if we take 1,024 and then simply we subtract 120 and then 45 and then 10 and then 1, we're going to end up with an answer of 848 as the total number of the total number of times, the total number of different combinations we'll have when we toss 10 different coins, and at least four of them are going to show heads. So again, we can go through the process of adding all these together, or simply we can take the total number of possible outcomes and then subtract the outcomes that are not in the set to get the outcomes that are in the set, which should be equal to 848. All right, that's it for combinations and not in math. Please join us in some practice problems and combinations in the next edition.